But it's great. But John gave a very good talk.
Oh, that's good to hear. Yeah, I think. Yeah, I was planning to watch it, but I think I my timing got messed up, so I ended up missing it. But
Mhm.
so
Yeah, yeah, and also John, because he presented some of the new research he's currently doing,
okay.
so he declined the filming. I think it's totally
Yeah,
fine
yeah.
because yeah, I also feel uh, grateful that a lot of researchers would like to present the updated research of what they are doing working on to us. So I really appreciate that. So I totally understand that don't film in some of the situations according to the concerns of the speakers. In particular, we are going to post them on YouTube.
Yeah.
So for published results is better. Okay. Now let's begin. I think there are
Okay.
more people going to join soon. So okay. So today is our great pleasure to have James speaking with us from Riverside, California. So James did his PhD at the Rice University, and so this is just one. Manually, this is one chapter of your PhD thesis, or it is not one chapter of your PhD thesis for the 2019 geoscience paper.
Sorry. Yeah, just a chapter from the thesis. Yeah.
Okay, I see. Because you in your acknowledgement you mentioned something about it. But I do know that rest of your work are high pressure experimental work.
Yeah.
But
Yeah.
yeah. So now James is a postdoc at UC Riverside and is still working on the project relevant to this topic, but in different uh, time in Earth history. So with that, I'll give the rest time for James. So please go ahead.
Great. Yeah, and thank you for having me. I'm excited to be here. And so today, what I'll be talking about is kind of this link between the surface and deep carbon cycles and how this link may have some implications for the history of oxygen and as well as carbon on Earth. And so just to kind of start off, this is when you think of the carbon cycle, you might think of figures such as this, where you can see many different reservoirs and fluxes of carbon between the different reservoirs and the terrestrial reservoirs, marine reservoirs, as well as biosphere. And we can see that there's different fluxes of carbon being transported between these reservoirs. And if you kind of look over here in the back, we see that there's also this flux for volcanism. And if you look at this number of 0.1, you can see that this flux is very small compared to other reservoirs and fluxes in the surface system. And so what this means is that when we think of the short-term carbon cycle on the time scales of maybe years to thousands of years, the flux from volcanism doesn't play a very big role in kind of regulating this short-term carbon cycle. However, kind of when we look on longer-term time scales, volcanism is the main source, main influx of CO2 into this entire surface system. So on the time scales of millions to tens of millions, hundreds of millions of years, volcanism becomes very important when we kind of think about the different reservoirs and fluxes of the carbon cycle. And so when we become interested in this long-term carbon cycle, people begin thinking about this deep carbon cycle where we can kind of see these fluxes and different reservoirs where we have carbon being subducted into the mantle in different lithologies such as sediment, the crust, and mantle, and they kind of reside in the mantle until they are released at different volcanic settings, and they can be released at settings such as arcs, arc volcanoes, ocean island volcanoes, which is something like you think of Hawaii or the mid-ocean ridge volcanoes. And so then it becomes, when we start thinking about the deep carbon cycle, these are the kind of fluxes and reservoirs that we are interested in. And so when a lot of people are studying the carbon cycle, they're very, people become more interested and specialize in either perhaps the different processes in the surface carbon cycle, while some people are perhaps more interested in the deep carbon cycle. But when we're thinking about different processes on Earth, it becomes important to think about how these two different cycles are linked, because we know that the products of the surface carbon cycle do get subducted back into the Earth's interior at subduction zones, and where there's different processes going on in the mantle, kind of altering that carbon and then releasing it at different volcanic settings. So it becomes important to think about how the surface carbon cycle is affecting the deep carbon cycle, and as well as how the deep carbon cycle affects the surface cycle. And so for the rest of the talk, this is kind of what I'm going to be exploring, is how these two, perhaps the relationship between these two cycles might play a role in the evolution of oxygen and the carbon isotopes on Earth. And so here, what I'm showing is the evolution of atmospheric oxygen through time. And on the y-axis, we just have the log PO2 of the atmosphere through time. And we can see that throughout the, through the Archean, the oxygen levels are many orders of magnitude lower than what we have at present day. And then we see around 2.4 billion years, this dramatic rise in oxygen. And people have called this the Great Oxidation Event, where we have the oxygen levels in the atmosphere rising by several orders of magnitude. But they don't reach present day values. They kind of settle at some intermediate value. And so I was talking about how I'm hoping to talk about the links between the evolution of carbon and oxygen. And we can just see through the just this simple photosynthesis reaction that carbon and oxygen are intimately kind of related. And so the evolution of carbon and oxygen in the atmosphere could be playing a role in affecting the other. We can also see the kind of relation between the evolution of oxygen and carbon through time if we look at the carbon isotope values of marine carbonates through time. So here on the y-axis, I'm just showing the delta 13C of marine carbonates through time. And so we can see that throughout Earth's history, there's kind of this baseline value of around 0 per mil. But it experiences these excursions, some negative, some positive. And we can see that kind of coincident with this great oxidation event, that there's this, the largest, most long-lived positive carbon isotope excursion beginning around 2.3, 2.4 billion years ago, is kind of coincident with the great oxidation event. And this has been called the Lomagundi event. And so we can see that perhaps there's this link between oxygen and carbon in the geologic record. And so the way that this relationship, one way that it's kind of been explained in the past, is that so there's when photosynthesis occurs, you are producing this organic carbon, and this organic carbon prefers to take up the lighter isotope of carbon, carbon-12. And so what happens is that when you start burying more organic carbon, you're going to release more oxygen, and you're also going to be kind of tying up much more carbon-12 in the carbonates, or in the organic carbon. So this makes the reservoir for which carbonates are formed become heavier. So we get this positive excursion. And so perhaps if, so this F org is actually, I didn't explain it, but it's the ratio. So carbon, when it's kind of drawn out of the atmosphere, could go into inorganic carbonates or organic carbon. And this F org is just that ratio. So it's the ratio of organic carbon to this inorganic marine carbonates. And so if we increase this amount of organic carbon, we can get this positive excursion, and we could also possibly get this rise in oxygen. However, when you kind of look into more detail at these two records, there could be some possible problems to explain both events by an increased F org. And so what I'm showing here in black is just that same delta 13C record where we can see the Lomagundi event starting around 2.3 billion years ago. And what's shown in red is this value called cap delta 33S. And so what this value has been used to kind of record is basically the oxygen levels in the atmosphere. And so this value is thought to be sensitive to these photochemical reactions. And so when you have values that are non-zero, this is telling you that you're having this mass-independent fractionation of sulfur. And this is thought to only be able to occur in atmospheres with very low oxygen levels. And so once we start to see this disappearance of non-zero values in this record, this is kind of what has been used to define the Great Oxidation Event. So once these values have gone to zero, oxygen levels have risen to a high enough level that this mass-independent fractionation of sulfur can no longer occur, and we only have mass-dependent fractionation of sulfur through time, and we only see these zero values in this cap delta 33S. And so what some researchers have observed and pointed out is that it looks like the rise in oxygen has actually passed some threshold before the onset of the Lomagundi event. And so if the oxygen is rising prior to this carbon isotope excursion, it becomes difficult to kind of explain both events by this increased F org. And so then it becomes important to kind of think about what are some mechanisms that could kind of explain this kind of temporal discrepancy. And so if it's not F org driving the Great Oxidation Event and the Lomagundi event, we're kind of curious about what other ways can we drive these two events. And so that's kind of what I'll be talking about for the rest of this presentation. And so this is just would be like a quick background on this production of both carbonates and organic carbon. And so what's thought to control the production of carbonates is the delivery of cations such as calcium and magnesium to the oceans. And so when we increase this delivery of calcium and magnesium through weathering of the continents to the ocean, we can stimulate precipitation of carbonates. And so this delivery flux of calcium and magnesium is controlled by the weathering of silicates. And so this weathering of silicates is thought to be sensitive to CO2 levels in the atmosphere. So if we have rising CO2, the temperatures will be hotter, and also we'll get more precipitation. So this will increase our delivery flux of these cations to the ocean, and it could essentially we'll deposit more carbonates, drawing more CO2 out of the atmosphere. And similarly, organic carbon, I'm just showing this with this black symbol in this figure, organic carbon is controlled, the production flux of that is controlled by delivery of nutrients also from the continents. And back in the Archean, probably the important nutrient would be phosphorus. And so similarly, if it's also controlled by this flux of phosphorus is controlled by weathering, then perhaps if we increase the flux of carbonate production as well as the flux of organic carbon production, then we can increase our total flux of organic carbon production without changing that F org. So we won't be changing that ratio of carbonates to organic carbon. So our carbon isotopes aren't going to change, but we can deposit much greater amounts of organic carbon just through this increasing of this total flux. And so we can possibly get oxygen to rise without any change in the carbon isotopes. And so for the rest of the talk, I'll also explain perhaps how are we going to then subsequently change the carbon isotopes after the rise in oxygen. And so just if we look at this equation where this flux of carbonates and in turn organic carbon is controlled by these perhaps the CO2 levels in the atmosphere, it becomes important to kind of think about what are some possible tectonic events that might be leading to increased CO2 in the atmosphere, essentially through increased perhaps emissions of CO2 at volcanoes. And so this is one of a more recent paper, and they're kind of looking at how essentially surface erosion events where we're eroding the continents could be playing a controlling factor in kind of the tempo of plate tectonics and mantle convection. And so what this paper is kind of proposing is that, so if we kind of look at the subduction interface, if you begin weathering the continents, you'll deposit a lot of hydrated sediments along this interface, and this will kind of decrease the amount of friction between these two plates, and it could lead to an increased rate of convection. And if we start increasing the rate of convection, we could increase the amount of CO2 emitted at volcanoes, and this could drive kind of a increased volcanic CO2 emissions to drive increased weathering. And so in this paper, they proposed that perhaps there was this, and other papers as well, they talk about perhaps around 2.5 billion years, there could be this rapid emergence of subaerial continents. And so if we get these kind of transition to much more subaerially exposed continents, we could deliver much more sediments to the subduction interface, and that could lead to perhaps increased volcanism due to this kind of lubricating effect. Also, there is this kind of period of glaciations as well around this 2.4 billion years ago, and this glaciation is thought to also kind of increase the amount of weathering. And I think you guys had Brendan Keller come and talk, and this is just a figure from one of his papers, and this value of delta 18O and epsilon hafnium kind of measured in zircons is thought to kind of reflect the delivery of this kind of continental weathering products to these kind of arc volcanics. And so we do see that kind of around the peak of the Lomagundi, there's this peak in this kind of perhaps weathering products contributing to this arc volcanism. And so it becomes interesting to think about perhaps this is one mechanism to kind of perhaps drive increased volcanism around this time, to drive this increased weathering. And so another possible mechanism to kind of increase CO2 emissions is perhaps this transition from something like a stagnant lid, where we only have perhaps these volcanoes fed by mantle plumes, to something like a more modern plate tectonics, where we have these long mid-ocean ridges and long arc volcanoes, in addition to these more ocean island volcanoes. And so if we have the kind of birth of much more volcanic settings, we could perhaps get an increased CO2 emissions. And so this is just kind of showing the zircon, the frequency of zircons through time. And this is one of the records that has kind of been used to perhaps suggest that there could be this kind of transition from a stagnant lid to more plate tectonics. And this is very highly debated, so I wouldn't want to say one way or another if this is actually happening, but this has been one of the mechanisms that has been proposed that could possibly lead to increased CO2 emissions. And so, as I said before, we could, if that ratio of organic carbon to marine carbonates doesn't change, but we just get this overall increase, we can increase oxygen without changing any carbon isotopes initially. And so what I'll move on to next is about how we can essentially fractionate carbonates and organic carbon within Earth's interior. And so if we kind of go back to this schematic, we have organic carbon and carbonates being deposited on the seafloor, and they get subducted into the mantle. And within the mantle, we have this kind of reduced organic carbon and more oxidized carbonates. Kind of due to their different redox states, they might behave differently and might have different undergo different processes within the mantle that might affect their perhaps residence time. That's kind of what I'm going to be looking at for the rest of the talk. And so what I'm showing here is just a pressure temperature diagram on the left. And this black line is the PT path of one of those kind of subducting slabs that I showed earlier in the previous slide. And so as you kind of go up to higher pressures, you're going deeper into the mantle and you experience higher temperatures. And so what I'm showing here in this red line is if you have a carbonate-bearing rock, once you go above a certain pressure and temperature, or a certain temperature is the controlling factor, is that your carbonates are going to begin to decompose and melt out. So essentially, what I'm showing here on the right is the percentage of that original subducted carbon that's going to be retained in the slab. So if we don't lose any carbon, we'll stay at 100%, and if everything gets lost, it goes down to 0%. And so once this subducting slab kind of passes that carbonated out boundary, we'll have essentially the wholesale melting of that carbonate, and it'll go into a melt phase and can become mobile and leave that subducting slab and perhaps return to the surface. And so once it passes this pressure temperature point, the amount of original carbon retained in the slab essentially goes from 100% to 0%, and that carbonate hosted carbon can now be emitted back to the surface. These carbonates can also undergo metamorphic decarbonation, and that's what I'm showing in this blue curve. And so with these blue contours and these values, these numbers are corresponding to the weight percent of carbon that can be hosted in that carbonate phase, such carbonate minerals. And so as you go up to higher temperatures, those minerals are going to decompose, but they don't decompose exactly at one point, but you can lose it over these contours and pressure temperature space. And so we just kind of tracked how much of that carbonate can be lost through metamorphic decarbonation. And so we can see that for this oxidized carbonate phase, as you subduct up to higher pressures, and kind of at these pressures and temperatures that are thought to be, when these things are released at these kinds of pressures and temperatures, they are thought to feed these arc volcanoes. And so perhaps at these arc volcanoes, you are getting a lot of carbonate hosted CO2 contributing to volcanism at these arcs. And in comparison, what we're showing here is what happens to graphite along this PT path. And so this, I'm talking about graphite now because as you subduct this organic carbon up to higher pressures and temperatures, it's going to essentially alter and metamorphose into graphite. And so these are some of the experiments that I was working on and some others were working on during my PhD to kind of look at if you start melting one of these slabs in the presence of graphite, how much of that graphite is going to stay in the solid rock and how much is going to be dissolved into the melt. And so we just kind of, we look at some of those experiments, and we have some formulations for the dissolutions, and we can calculate that along this PT path, taking into consideration how much melt is being formed and how soluble the graphite is in those melts, we can calculate how much of that initial graphite is going to be retained in the slab. And so we can see that in comparison to the carbonates, the graphites are much more refractory. They're going to stay in the slab much more efficiently at these kind of sub-arc conditions. And so what this is kind of suggesting is that as we're subducting one of these slabs containing both oxidized or inorganic carbonates, as well as this more reduced graphitized organic carbon, when it reaches these subarc depths where we're kind of we're losing mass from the slab, producing melts or fluids, and contributing to arcs, most of that CO2 is likely to be derived from carbonates rather than organic carbon. And this is important because carbonates are actually, they have a very different delta 13 signature relative to organic carbon, and organic carbonates have a much higher value compared to organic carbon. So perhaps the delta 13C, and so I put this -5 because that's kind of the canonical value for just, there's thought to be this kind of primordial mantle carbon that's perhaps just been in there from the birth of Earth. There's just this carbon reservoir that's been in the mantle since that time, and that value is thought to be around -5 per mil. And these carbonates, as I kind of showed in that first figure, there's this baseline value of around 0 per mil. So if you're getting a lot of carbonates emitted at arcs, we might get CO2 emitted with delta 13C that's at greater than -5. And so what I'm showing here is a compilation of delta 13C measurements of CO2 emitted at some of these different arcs around the world. And what they, when they kind of look at all these measurements around the world, they get this global arc average, flux weighted average of delta 13C to be around -3 per mil. And that is more positive than this kind of canonical -5 value. So this could be suggesting that perhaps these arcs are being sourced by carbonates, preferentially to primordial carbon as well as organic carbon. And so one other thing that becomes important to, if someone is proposing that these volcanoes are emitting carbonates, it becomes important to kind of think about, are these carbonates being sourced from the subducting slab, or could they be carbonates that are picked up as these magmas are migrating through continents? Because a lot of continents could have these thick carbonate deposits. So this signature could be telling us about the continents rather than something from the slab. And so what this figure is showing is we kind of use this to kind of investigate that question. And so what is shown here in the x-axis is the F-org of the sediments entering that some trench, and the delta 13C of CO2 emissions at that particular arc. So we can see that as the sediments entering a specific trench become more organic rich, there does seem to be this trend that as the subducting slab is becoming more organic rich, the delta 13C of the CO2 emitted at that arc is becoming more negative. And so that's kind of telling us that perhaps the ratio of organic carbon to carbonates in the subducting slab does play a controlling role in the CO2 that's emitted at a particular arc. And so I was talking about perhaps this scenario where there's this large contribution from the upper plate rather than the subducting slab. And so I marked here in orange, these are volcanoes that are arcs that are kind of passing through. They're known to pass through these very thick carbonate sediments, and that could be kind of pushing them off this trend just because of that large contribution of assimilated carbonates from the upper plate is going to shift you up. And so that's perhaps why they lie off this trend. But if you look at the blue curves, blue data points, it does kind of show that perhaps there is some control of this subducting slab on the CO2 emissions. And what I'm showing here in this dashed line is, so it's just a linear trend from 0 per mil at 0% organic carbon to minus 25 per mil at 100% organic carbon. And organic carbon is thought to be, kind of on average, maybe around minus 25 per mil, and carbonates are around 0 per mil. So if we kind of have equal efficiency of release at different F orgs, then if they were released with equal efficiency, they should lie on this curve. And if you're above this, that's telling you that that would suggest preferential carbonate release. And if you're plotting in this region, it would be preferential organic carbon release. And it does seem that many of the data points are kind of shifted more dramatically to this region of preferential carbonate release, kind of suggesting that perhaps that indeed perhaps we are releasing carbonates more efficiently relative to this kind of graphitized organic carbon from these subducting slabs. And so now the picture is that we have this kind of subducting slab that's lost this carbonates, that's releasing this CO2 with this high delta 13C. And now we have a subducting slab that's kind of been stripped of the carbonates, but it's still hosting much of the graphitized organic carbon. And these subducting slabs are going to subduct deeper into the mantle, perhaps at the core mantle boundary, and perhaps become entrained in these upwelling mantle plumes, where they can become, they're going to rise through the mantle and kind of contribute to melting at some of these ocean island volcanoes. And due to the high extensive melting, and also these regions are thought to be highly oxidized in the upper mantle, we can reoxidize that graphitized organic carbon in this kind of intense melting region at higher oxidation states, and that can release this graphitized organic carbon that might have a more negative delta 13C signature. So perhaps these ocean islands are emitting CO2 with more negative signature. And so this is kind of this delay between the different forms of carbon within the mantle. And so it becomes kind of important to think about, is there any way to, is there any data that would support the idea that these ocean islands are kind of emitting CO2 with more enriched in organic carbon? And so what I'm plotting here is diamonds, which are just going to be pure carbon from deeper portions in the mantle. And so I was talking earlier about this kind of more primordial mantle carbon. And these are thought to be hosted in a rock kind of called peridotite. And so we can see that you can see that this is where this kind of canonical mantle value comes from, this -5 per mil from these peridotic diamonds. Now, eclogitic diamonds, eclogite is a rock that's kind of the metamorphosed or subducted oceanic crust. So it's kind of rocks that have some origin from the surface. And you can see that they are mostly kind of, there's the largest peak around -5 per mil, but it does have this tail off to more negative values. So perhaps these diamonds that are kind of hosted in this eclogitic rock, which is thought to be coming from the surface, perhaps being influenced by organic carbon with this more negative delta 13C. And we can also see that if we look at lower mantle diamonds and transition zone diamonds, they do have these populations at these more negative values, perhaps suggesting that this deep carbon could be sourced from surficial organic carbon that's being subducted past the arcs into the deep mantle. And also, we want to look at perhaps the CO2 being emitted at these ocean islands. Is there any evidence that they might be emitting light delta 13C CO2? And so this record the measurements are much more sparse compared to the arc measurements, but this is just a compilation of what we've kind of found in the literature. And it's important to point out that we plot all the data from specific sample set, but these measurements made at Kulau, Society, Loihi, and Pitcairn, they're made on glasses. And the thing about volcanic glasses is that, so the thing about CO2 is that it has a very low solubility. And so by the time these magmas erupt and are preserved as a glass, they've lost a lot of their CO2, so they've degassed. And that degassing process is known to fractionate these carbon isotope values. And so what we do is we plot the least degassed sample with a star. And so if we just kind of pay attention to some of these less degassed samples, there is a possibility that some ocean islands are emitting more negative values relative to the arcs in mid-ocean ridges. And this one data set from Kilauea is one of the data sets that was made on measurements on these high temperature gases. So they are more directly comparable to this arc data set, which were all measured in these fumaroles. And you can see that perhaps they are slightly more negative than what's being emitted at arcs or mid-ocean ridges, perhaps suggesting that there could be some hint of organic carbon in their source. And so the way that we're proposing that one way to drive these long-lived carbon isotope excursions is that initially you're going to release, you subduct this increased load of carbonates and organic carbon, and then you're going to release much higher amounts of this carbonates initially. And so this overall balance of CO2 is shifted to carbonate values, which are more positive. And so if the reservoir, this influx of CO2 into the atmospheric reservoir is going to become heavier. And so in turn, the carbonates that are being produced from this heavier atmosphere are going to also increase. And so you get, as long as you're releasing these carbonates, you get this rising limb of a positive carbon isotope excursion. And once there's this delayed release of the organic carbon with these more negative values, more negative delta 13C values, that can kind of bring you out of that positive excursion because you're now balancing this increased flux of carbonates with an increased flux of organic carbon. And so then it becomes important because that kind of time scale of our carbon isotope excursions are going to be related from that travel time of essentially the release of that organic carbon. So some subducted slab that's kind of, this is just a simulation from the paper, this Lee and McNamara, where they're kind of interested in how long does this subducting slabs kind of spend at these core mantle boundaries? Because there's the ideas that perhaps it subducts to the mantle and this kind of stagnates there, and it's been called like a slag graveyard. Perhaps they just subduct and stay there forever. So these authors were interested in essentially how long does that subducted oceanic crust kind of stay at the core mantle boundary. And essentially, I think, let me see, this was it had a video done. How do I yeah, so what you can just kind of see they're tracking in this bottom figure, you can see this green or teal value is the subducted oceanic crust. So you can kind of see it subducts and it moves over and it's kind of released back to the surface, and it doesn't seem to kind of stagnate too long at the core mantle boundary. And it's kind of thought to, these convection cells kind of form some kind of symmetrical cells. So what is happening, it's down to the core mantle boundary is about 3,000 kilometers. So if it travels down 3,000, across 3,000, and up 3,000, that subducted oceanic crust is going on the order of 10,000 kilometers. And the plate speeds are thought to be, so as we can measure the movement of plates on the surface, and that's thought to be equivalent to the speed of mantle convection. And those plate speeds are on the orders of 1 to 10 centimeters per year. And so if it's traveling a distance of 10,000 kilometers, that time scale comes out to 1 billion years to 100 million years. And we know that the Lomagundi, that duration is about 2 to 300 million years. So perhaps that duration of the Lomagundi could be in the realistic time scale of this mantle convection, kind of suggesting that this process could be controlling that length time scale of the Lomagundi event. And so then the kind of we, after looking at all this, these observations, we wanted to just put together a simple box model to kind of see if we make some of these assumptions that we're developing from these observations, would that box model kind of reproduce some of the features seen in the Lomagundi and the rise and the Great Oxidation event. And so these are just some of the, I want to walk through some of the important assumptions in that model. And so in that model, we have the flux of carbonates, the production of carbonates is controlled by an equation controlled by the concentration of CO2 in the atmosphere. So as we get more CO2, that flux is going to increase. And we're going to keep the fraction of organic carbon to inorganic carbonates constant at this 0.2, which is kind of this canonical value that will give you this 0 per mil for carbonates. So throughout the model, we don't change that. We keep it constant at 0.2. So any of the carbon isotope excursions are not driven by this change in F org. And we're tracking also atmospheric oxygen, so that's proportional to just the mass organic carbon in all of the reservoirs, and that's just due to this photosynthetic production. As you bury organic carbon, you can accumulate oxygen in the atmosphere. And so we're tracking the delta 13C of CO2 released at different volcanic settings. And so we have a flux from mid-ocean ridges. It's thought to be this primordial carbon that's kept constant at this -5 per mil. This carbonate, this arc values, this arc flux is going to be strongly influenced by the carbonate value, the delta 13C of these subducted carbonates. So this value is going to be largely or mostly greater than -5. And we also have the CO2 being emitted at these ocean islands, and that's going to be influenced by this graphitized organic carbon. So it's going to be releasing CO2 with a more negative delta 13C. And we're also assuming that carbonates are released on the order of tens of millions of years after subduction, while organic carbon is released on the order of 100 millions of years after subduction, just based on this kind of this mantle convection timescale. And so those are the main assumptions that kind of go into the simple box model that we presented. And so this is just what is some of the results from that box modeling exercise. And so what I'm showing here in the top is the carbon isotopes. This is just that data from the earlier figure. In this blue is the atmospheric oxygen through time. This is these are both estimates. Both the blue, darker blue, and light blue curves are estimates of oxygen through time. And what I'm going to be showing down here on the bottom is these CO2 fluxes for both this red dashed red curve is carbonate and organic carbon production. This kind of weathering flux or production of carbonates on the seafloor, as well as the CO2 fluxes at different volcanic settings. And so these orange curves are going to be are the model results. And so to start off with, we are just running it, and what we're prescribing in these runs is just the mid-ocean ridge CO2 flux, and these ocean island and arc fluxes are responding to that. And so initially we just run it to at a steady state, and we get a stable delta 13C and stable PO2 in the atmosphere. And then what we do next is we increase the CO2 emissions at mid-ocean ridges. And so what happens then is that due to that increased CO2 in the atmosphere, our carbonate and organic carbon flux increases. So we're depositing more carbon on the seafloor. And shortly after, that arc flux responds to this increased subduction flux of carbonates. So we can see in the blue curve that shortly after, this arc flux responds to the increased mid-ocean ridge flux. And due to that, and just due to this increased organic carbon, we have a rise in oxygen in this curve. And due to the emission of more carbonate-derived CO2 at these arcs, we get this increase in the delta 13C of marine carbonates. And this is just to point out that we can, due to this delay between the precipitation of carbon on the seafloor, as soon as you deposit that increased carbon with organic carbon on the seafloor, you're going to drive oxygen up. But we don't increase the delta 13C until that carbonate is deposited, subducted, released from the slab, and then emitted at the arcs. So you can get a delay between the rise in oxygen and the delta 13C positive excursion, known as the Lomagundi, which has kind of been observed, this initial rise in oxygen prior to the carbon isotope excursion. And so due to this imposed delay time of this organic carbon on the order of hundreds of millions of years, that response of this increased subduction flux of organic carbon doesn't respond until hundreds of millions of years later. And once that ocean island flux increases, we're starting to emit more negative delta 13C, so that overall CO2 emissions goes back into balance between this carbonate and organic carbon flux, bringing us out of the positive carbon isotope excursion. And so I guess just to kind of conclude, we're proposing that perhaps the Great Oxidation event and Lomagundi event can result from tectonically driven increased carbon deposition and the deep recycling of organic carbon. And this kind of mechanism that we're proposing can also be consistent with the delay between the rise in oxygen and the carbon isotope excursion, as seen in the great oxidation event and the Lomagundi event. And an important thing to note is that perhaps the carbon isotopes of CO2 emissions at different volcanic settings may vary systematically based on what kind of carbon they're sourcing. And we can now we provide an alternative interpretation of these large, long-lived positive carbon isotope excursions that they can be driven by this mechanism instead of these changes to F org. And it's just kind of points out that oxygen levels and biomass production on Earth could be have a strong control by solid Earth tectonics. And I think maybe I'll stop there. And thank you for your attention.
Okay, thank you, James, for your presentation. Now it's time for questions from the audience. So when you ask a question, please let us know your name and your institution. So go ahead, feel free to open your mic.
Hi, this is Xiaoming from UNC Chafei. Can you hear me?
Yeah, I can hear you.
Oh, okay. Yeah, it's great talk. And also it's very interesting paper. I was wondering, why did you stop at about the Metaproterozoic? Is there any other?
I think, well, so yeah, this is one of the things that I'm working on now. I'm looking at the Neoproterozoic. I think it's just, for this paper, we were just kind of interested in looking at just this single, great oxidation event and Lomagundi event. But definitely, I think when you kind of look at the Neoproterozoic, there's kind of this, it's almost like a mirrored signal in the records. And so that's what we're exploring now, is to see if that mechanism might also make sense in the Neoproterozoic. And that's what I'm kind of doing over at Riverside. That's what I'm looking into now.
Oh, cool. Okay, that's another question. Follow up, I guess. What's your plan next? Seems like this model you already did pretty well. But is there any uncertainties you can put on? I guess in your paper I saw uncertainties. I guess here you did the curves.
Oh yeah, here there's like in the paper we look at, it's like a sensitivity analysis to see how the model will respond to changing different parameters, such as the time scale or the residence time of different forms of carbon in the mantle, the residence time of carbon in the continents. In this, I think in this model we're assuming that there's like 100% release of carbonates at the arcs and 100% of organic carbon at the ocean islands, but it's most certainly not the case where it's 100%. That looking at how those ratios would change the model outputs. And so, yeah, I think we weren't so set on developing the model to perfectly match all the magnitudes. It's more looking at, in this paper, we're just looking at the mechanism and the overall behavior to see if it would make sense. Yeah. So yeah, moving forward, perhaps looking at more of the uncertainties and looking at how it actually compares to some of the magnitudes of different events would be something that interesting to look into going forward.
Cool. Thank you so much.
Thank you.
Okay, I would like to ask a question relevant to the carbon isotopes. Actually, for the carbon isotope, there are fractionations in Earth's interior, not only limited to the carbonate and different silicon minerals that could cause the carbon fractionation, but also including the diamond formation process itself. The kinetic fractionation could produce a wide range of Carson isotope distributions. So in your model that I don't think that you really consider that. So what is your view on that? Or if you could consider in the future, that how would you incorporate that into this consideration? Or you don't think that carbon isotope fractionation matter in the Earth's interior matters for your model?
Yeah, so that's definitely true. Yeah, what we're in this model, we're not having any alteration of carbon isotopes once it's kind of been introduced into the mantle. And as you pointed out, there is most definitely going to be some fractionations during these processes. But so I guess one of the things that is interesting when you look at this kind of carbon isotope record through time is that there seems to kind of be this baseline of 0 per mil through time. Like it doesn't really, there's no trend through time. Like we don't see an increase or decrease through time. It's kind of around this 0 per mil. And so I think what that is suggesting, we know that we're probably subducting organic carbon and carbonates. And so if either we're preferentially, so if one is perhaps stored in the mantle, I guess, if you would say forever, then we would see this trend through time change. Like if we were preferentially storing organic carbonates or organic carbon, graphitized organic carbon, then we would essentially be drawing light carbon out of the surface reservoir forever, and this would kind of be increasing through time. It wouldn't be exertion, so it would kind of go up. And so I think that the easiest way to explain that is that there's kind of wholesale or complete release of both organic carbonates and carbonates through time. And so if we're kind of assuming that they're released at this 100% efficiency through time, then I guess those fractionations would become less important because you're essentially releasing the whole reservoir. But yeah, it would be important to kind of, we could add that into the model, just looking at perhaps how the fractionation events in the mantle would affect what's being emitted at the volcanoes. That's definitely something to consider. And I know that there's some experimental data to look at that we could try to parameterize into the model. Yeah.
Yeah, because including the phase diagram you put on in the carbonate out, that one is compositional dependent first. That
yes.
Depending on the composition of the carbonate has been put on. Actually, it also depends on how this, let's say, the carbonate, like say, reaction with silicon minerals that also will control composition. Furthermore, like say, the geothermal evolves with time. That is not always at 3 GPa in there. Earlier, it's probably harder. It could be shorter, let's say, shallower than that, and later on that it dives deeper. What I see is that the carbonate is more like is less than a line, but more like a zone. Is a composition dependent zone. That for the carbonate out, that could be considered in the model. But I think that is just one thing. I agree with you. Yeah, if you look at the gas in, gas out, you put that phase, you put that, I would say, that threshold or that plane or curve at the Earth's near surface, then the mantle fractionation doesn't matter.
Yeah. That's I think that was one way we could justify the way we put it, but I think that's just, we just wanted to, for the first round, to make it as simple as we could, but definitely as we go forward, adding some of these complexities, looking at fractionations. And yeah, so like what I showed in that diagram, it was if you're interested, it was just for subducted sediments. It wasn't like an oceanic crust, all those calculations. So yeah, if we change the lithology, then it's gonna change. And that PT path, it was adjusted for mantle heating through time. So I think there was, I can't remember exactly, but it would be hotter than an average PT path on present day. But that's also something that's going to play play a role in how efficient these different forms of carbon are released, and would be important to look at, maybe moving forward.
Okay, James, thank you again for giving the presentation and for the interaction. Okay, thank you everybody for participating on Sunday morning in China, although it's the national holiday. It's a 8-day vacation for
Oh,
most
wow.
people.
Hope you enjoy the holidays, man.
Yeah, at least we could get around outside now because theaters are open.
Oh, wow, that's great.
Yeah. And what is bizarre is that this is a busy time for the weddings, because
okay.
the weddings that since earlier year has been accumulated. So this is a long vacation. So my parents, they attend 8 weddings during
Oh
the
my
vacation.
God.
So one wedding every day. So yeah. Even in the community I live in, I see people are going to get married. There are wedding going on today. Yeah.
Oh, wow.
Okay.
Yeah. Thank you again for inviting me. It was a pleasure.
Yeah, it's great interacting with you. Okay. Thank you, James. Thanks, everybody. Bye-bye.
Bye.